We're going to continue talking about finite state machines and non-deterministic finite state machines, and in general, how you convert one to another, and this idea that we began talking about last time, this idea of having these machines be closed under some kind of operations, in the sense that if you can figure out a machine for one set, you can figure out a machine for its complement. If that's true, we say that these finite state machines are closed under complement. So that way, if you get a particular set, you're not sure whether it's regular or not. I used to use the word regular. Regular means that there's a finite state machine for it. It's just a term people use. And you'll see why they call it regular. Regular because these strings tend to grow in regular intervals. But they're called regular sets. So regular sets are closed under some operations. And the more of these closed operations you know about, the easier it's going to be for you to determine whether a set is acceptable by a finite state machine or not. And we talked about complement, and we talked a little bit about reversal. We're going to talk more about that reversal today, and it'll help us review non-determinism, and it'll help us review those E-moves that Dimitri talked about, and talk about union and intersection as well, as far as what sets get accepted. Okay, so let's do an example we did last time. It's the binary strings. Every one has at least 2 zeros following immediately after. The reason I want to go over this is, number one, is just another review of an example of a finite state machine, and to remind everybody how to do it. And then, once we write this machine up on the board, we're going to try to make up a machine that accepts the reverse of this language. How would you describe the reverse of this language in English? The reverse of a language is take all the strings in the language and reverse them. And that's the reverse of the language. So how would you describe in English all the strings in the reverse of this language?
It's preceded by at least 2 zeros.
Okay, everyone is preceded by at least 2 zeros. That's exactly right. Because if everyone is followed by at least 2 zeros, and if you reverse all those strings, it's all the strings where every one that shows up has at least 2 zeros in front of it. Now, it turns out if I started with that problem, it would seem a lot harder than this problem. This problem, we're going to have our finite state machine kind of move left to right. And every time we see a 0, we're going to keep track of what to do next. It's very natural to write this solution up, and we're going to do it in 2 minutes. But the other one is a little tricky. Every one has at least 2 zeros preceding it. Your gut instinct is, well, how do I know if I'm supposed to be counting the 2 zeros or more until I see the 1? Then if I see the 1, maybe it's too late. I don't know if I've seen the 2 zeros. And that gut instinct is actually wrong. It is easy to do that other one, but you might not be able to figure it out at first glance. The fact that knowing a finite state machine for a set allows you to figure out the finite state machine for its reversal will make that second problem a lot easier. We'll be able to do it mechanically. Once we know this one, we can mechanically convert it to one that does its reverse. And that's an advantage of understanding these closure properties. In doing this reversal, it's going to be a very nice general idea of how to reverse any machine, but in doing it, we're going to come up with non-determinism again. And it's a good motivation for non-determinism. That's what we'll do for the first 20 minutes or so today. Okay. Guys ready? Okay. Erica?
Hello.
Good morning. We're doing this machine. Everyone has at least 2 zeros following immediately after the 1. So I want you to help me do this. Okay, so we're starting in this state, and we're reading a string, and we want every time you see a 1 for there to be at least 2 zeros afterwards. So help me out.
Oh, me personally?
You personally. Yes.
Oh, well.
So that way, if you like to be called on, you should always come in late.
I see. Well, if we see a 0, then we can come back to the same place.
Okay, right. If you see 0, you don't care. Nothing interesting's happened, so you don't need to store any new information. So we stay in the same place. This is basically, I got nothing interesting to store here, so I'm just no information. And if I see a 1, I go someplace else because I got to remember. If you think of this as far as programs go, you know, it's kind of like different lines in your program, different places in memory. I mean, if you see a 0, stay where you are. Otherwise, you know, if then else, go to this set of lines. So here's the then else. And So this means I've seen a 1. I just saw a 1. So now what has to happen?
You have to get a 0.
More than 2 zeros.
Well, right, but
Okay, okay.
yeah. So if you get a 1,
One step in front of the other. Yeah.
dead.
If I get a 1, I'm dead. Good. Here's a dead state. Nothing will ever get accepted that ends up in there. A 1 takes me to a place that I don't want to accept, and then any symbols just leave me there. And if I get a 0, somewhere else, not in the same place.
No,
Why not?
because you have to count.
Because we have to count 2 zeros. Right. If we went to the same place, then we'd count 1 0, right? And, yeah, well,
You could do it 2 or 3 zeros, and then you'd get a 1, and that should be okay, but it's not.
right. You'd get 2 or 3 zeros, and then you'd get a 1, and you'd see you're dead, but you're not supposed to be dead. So we need to actually count 2 zeros. So here's 1 0, and here's the second. This is good. I'm going to put a final state here. That's a good thing. We got to fill in some 1s that we left out. What happens when you get a 1 here? Dead, right? Because you need 2 zeros.
But a 0 should take us back to the first state, and that should be valid.
Not necessarily, because the empty set doesn't. I don't know. Can you have the empty set?
What do you guys think? According to this definition, should I accept the empty string?
Yeah.
There's no 1s in the empty string, so it's vacuous. So Chris is saying that he doesn't like going to a new state here for the second 0 because he wants to think of this state as everything's okay so far, and I didn't just see a 1. And the everything's okay so far and I didn't just see a 1 is already embodied in our initial state. Everything was okay so far and I didn't just see a 1. Now it doesn't hurt to do this. I mean, in some sense, Chris is wrong for saying, no, don't do it that way. But he's right in that this would just be a finite state machine that's bigger than I need. I could definitely make this smaller. And keep in mind, there is no one finite state machine to accept a set. There are an infinite number. There is one unique minimum 1. And the way I have this now, we're not going to get the unique minimum 1. So if I want to get the unique minimum 1, and that should be your goal, then I should do what Chris says, which is to reuse this state instead of this. So I basically notice that this state is identical to this. And now this state becomes the final state. Okay. Is that okay so far?
What about
Teresa?
the start state, though? He's like, you finished as soon as you started?
You can, if you start and you don't see anything, if there's no symbols to look at, like if
Why
you,
is it accepting that?
because it's supposed to accept empty strings. There's no 1s there.
Supposed to accept an empty
Yeah, because this is only if there's 1s, there have to be 2 zeros. So if there's no 1s,
It's-
there's no condition, and an empty string has no 1s, and it's okay. So it's okay to accept the empty string.
It also accepts strings of zeros of any length.
Right, and it'll also accept strings of any number of zeros as well, which you want to do. You want to take lots 0, 0, 0, 0, 0, 0. Those should all be accepted. They have no 1s in them.
Why is that? I'm just looking at what the sentence you wrote. You said everyone is. I thought you were only going to accept that, but there were some other assumptions we were going to accept. You could
No.
say if there's a 1, everyone has at least.
Yeah.
Oh, so that.
If
If there's not a 1, then
If there's not a 1, then it's fine. It's just that if there's a 1, there must be 2 zeros following it. All right. So does this look all right? Anything else we have to do? This is not an accepting state because we haven't seen the 2 zeros. That's not an accepting state because we haven't seen 2 zeros. That is an accepting state because we have, and that's a dead state. All right, so I want to, this is the minimum 1. But I'm going to do this for a second. This is what I was going to do originally, and I'm going to stick with this, even though it's not minimum. This machine is equivalent. It does the same thing.
it's a 1 that's actually.
One should be going.
Oh, sorry, this is not a 0, 1, right?
It
Sorry.
should be going to the next.
And it should be going back to here. Now we're right. If you look at this state and this state, they're identical in their function. A 0 sends them back to themselves, and a 1 sends them over to here. So when I come out of here in a 0, why go to something that mimics exactly what this does? Why not just go directly to the actual state? So does everybody see that this machine is equivalent to that more minimum one, and it's just a little redundant? These two states are equivalent, and together they're part of like one class of equivalent states, and they should just be one state. But I'm actually going to leave it like this because the example that I'm going to do next becomes a little more involved and more general if I have a machine that's bigger. So just for pedagogical reasons, let's leave this bigger machine up there rather than the smaller machine.
That machine is clearer than the smaller one.
Maybe. It depends how well you describe the meaning of the states. If you say that this state means I haven't just seen a 1 and, well, the last symbol I saw was a 0, then I think it's okay. Well, I don't know. Maybe you're right. Maybe it's clear. All right. So here's what we're going to do. We're now going to go ahead and try to reverse this. We're going to try to make a machine that accepts the reverse of this language. That means every 1 has at least 2 zeros immediately preceding it, rather than 2 zeros coming after it. We're not going to try to do this deterministically straight up, because it's a nice exercise, but it's not what I want to do right now. What I want to show you how to do is how to reverse any machine completely mechanically. And in doing that, it's going to bring up other issues of non-determinism and stuff we talked about before. So let's look at this machine and think of it as a general, any machine, any finite state machine. How could we change it? How could we fiddle with it? How could we do surgery on it so that when we're all done, it accepts exactly the reverse of the strings that it used to accept?
It's hard to know even what the reverse is.
Let me define it specifically. The reverse of a language, of a set of strings, is take each string, reverse it, and that new set is the reverse of the language.
But I would almost think that it would be where every 0 is followed by 2 1s or something.
Well, because here, but that...
You just write out an acceptable string and you flip everything.
Well, let's hear it. 1 0 0 is definitely in this language, right?
Right.
Therefore, 0 0 1 needs to be in the reverse of the language.
Okay, so every acceptable.
And a 1 doesn't have 2 zeros after it. What you're saying is sometimes defined as the dual, where you're switching a 0 for a 1 and a 1 for a 0. That's not what we mean by reverse. We don't mean switch a 0 for 1 and 1 for a 0. We mean very specifically just reverse the order of each string.
You can go through all those words at some point later on, like duals and reverses.
Yeah, dual is actually not used so much, but yeah. It isn't even, reverse is just defined, it's not even a very important term either. But
so it's kind of like you're just changing the direction of the logical implication rather than taking the complement of the whole statement.
You're not taking the complement, right? You're changing the order of the strings. So the complement would be all the things that are not in the set. And that's different than reversing each string. All right, but Chris, you get the actual definition.
I think I
yeah.
Not trying to transform the sentence, but look at an example string and transform that, and then construct a new sentence from it.
Exactly. Take the set of all the strings, reverse each one. That new set is the reverse of the original. Absolutely.
Are there a whole set of operations we're going to study reversing?
You know, for every new exam, some professor makes up some new operation. There's reverse, and there's star, and there's concatenation, and there's min, and there's max, and there's prefix, and there's suffix, and there's half, and there's log, and there's square root, and you can go on and on. You can make them up. One point, I think in the late 60s or early 70s, probably late 60s, there was a paper that basically said, here's all the things that finite state machines are closed under. Not all of them, but a lot of them, and try to characterize them. And for your own knowledge, finite state machines are pretty much closed under anything you can think of, except a few things. So, clear as mud, yeah. Well, the truth is you're pretty safe with finite state machines. They're closed under most things. The other levels we talked about, especially the levels between finite state machines and Turing machines, are not closed under everything. But finite state machines are closed under most things. And
What do you mean by that exactly?
oh, all right. Backing up. Any set that has a finite state machine that accepts it is called a regular set. Okay, it's got a name. So from now on, instead of talking about finite state machines, I'll call them regular sets. Regular sets are closed under some kinds of operations. And what that means is, if I do the operation on the set and I get a new set, for example, I complement. I take a set, and then I take all the things that are not in the set. I've done an operation on the set. I've created a new set. It's complement. If that new set is also a regular set, always, without any exception, then we say that the collection of regular sets are closed under complement. That you can take the complement and you just get another regular set. All right? So that when you do the operations on these sets, you never get something weird outside the club. You always get something in the club.
It'll take a different finite state machine.
A different machine.
Accept it, but it can still be accepted.
It might even be the same finite state machine if you really got a peculiar example. But, right, usually a different finite state machine, but it has to be a regular set. There will be some finite state machine.
So by outside that world, you mean something like being uncountable? Or
Something like being a context-free set or a Turing machine level set. Something like there's no finite state machine that ever would get it. So if you take the complement of a set that comes from a finite state machine, there's always a finite state machine that accepts it. In fact, that's an easy proof. We talked about it yesterday. Here's a finite state machine that accepts this set. What's a finite state machine that accepts its complement? The answer is take the final states, turn them into non-final states. Take the non-final states and turn them into final states. Just toggle the final and the non-final state. So everything that used to get rejected now gets accepted, and everything that used to get accepted now gets rejected. So the new machine accepts the complement of the machine that this represents. So regular sets are closed under complement. So if you can think, if somebody gives you a problem and you can't figure out how to do it, but you know how to do its complement, so just do its complement and then mechanically convert it. Same thing with reversal, and same thing with many, many, many other operations. Union, intersection, and lots.
In the case of this example, the regular set would be out of any binary number, the set of all binary numbers that have at least 2 zeros falling into 1. That's the set. It's the actual.
Yes, the set is all the binary strings that anytime there is a 1, there are at least 2 zeros that follow it. And now we're discussing the reverse of that set. We're wondering whether you can always get the reverse of a set using a finite state machine. Maybe reverse gives you something that might be hard to do, but it never does. Regular sets are closed under reversal. If you take a regular set, a finite state machine, and you reverse the set, you can always get another finite state machine that accepts it. And we're going to go through it right now, as soon as everybody makes sure they understand reversal, and I go through all the rest of the questions.
Could you say one more time what a regular set was?
A regular set is any set that you can make a finite state machine for.
Okay.
If you make a finite state machine for it, it's a regular set. We're going to characterize these sets a little more carefully. I mean, regular sets are really well understood. There are machines that describe them. There are things called grammars that describe them. There are things called regular expressions that describe them. You've all played with regular expressions, right? They have it in all these web development tools. When you're searching for patterns, you say, I want this star followed by this, followed by... So that's another way of actually describing these kind of machines, a different way. And we're going to show an equivalence between all those ways later on and really nail down finite state machines and regular sets as best as they can be. Yeah, Teresa.
Theoretically, did all this technique exist before computer science, and what was it used for?
Yeah, Neil asked this yesterday, and it's a very good question. This stuff, finite state machines as a theory and context-free grammar is the next level, and Turing machines as a theory, started at different times. The earliest reference to a Turing machine, I think his paper, Alan Turing's paper, was in 1936. That was pre any computer. Not pre the idea of a computer, perhaps, but pre any built computers. This stuff was done in the 50s primarily, and early 60s, and 1960s, 1950s, and the context-free grammar stuff was done primarily in the 60s and late 60s, maybe early 70s. So it was more or less parallel in the development of computers, this theory stuff.
Okay, it was developed for this purpose, pretty much.
Well, no, I think it was developed mainly as a mathematical subject of kind of intellectual interest to kind of model the notion of what computation is. And at the same time, we had the serendipitous application to compilers and programming languages. So people worked on that at the same time.
Did a practical problem push this, motivate this?
I don't think so. No.
Chomsky's work did in the 50s to show that this was insufficient for human language.
From a linguistic point of view, right.
And that's what
Yeah, actually, this bullseye I showed you the other day, finite state machines and then context-free grammars and then Turing machines, that more or less is called the Chomsky hierarchy, which he must have done in the mid-50s. Yeah. Brian.
So I have just a word question.
Yeah.
I'm wondering, maybe you'll know this, the term computation, did it mean the same thing before computers? Or rather, I wonder where the term came from, or if it sort of originated around the time we started building machines that did this sort of thing.
I don't know the answer. I mean, it's a good question, the actual origin of the word and how it was used. My sense is that computation was used in the same way we think of it now, long before computers were used. When Alan Turing tried to abstract away, what we meant by computation, it was the first attempt to describe it rigorously. We all had a notion that there was a difference between thinking and logical kind of argument and brute force computation. So he abstracted away all the issues and said, okay, here's what we mean by computation. You need to come up with something like this. This is a computation. Anything else that you can't describe this way, that's too vague. That's not computation. So I think, in some sense, the word got a rigorous meaning only in the 30s and 40s of the 20th century. And before that, it was left vague.
But did Turing actually use that, the word computation?
Yes. He definitely used that word. Yes, yes. It's in the title of his paper. I forget the name. The paper's in German, so I don't. Not in German. I forget the name of the paper. It's in English. Ooh. Ask Patrick Winston that when he comes. That's a really good question. It's there's a lot of different camps in AI, and a lot of different camps outside AI, and there you're going to get into real verbal battles, because you're getting into philosophy. At least here we can always be grounded in something very specific. But it's a big question that I really...
Could like cement one end of it.
Yeah, well, this reminds people a little bit of neural nets, this idea of modeling, the 10 to the 9th neurons in your brain by inputs and outputs, and just getting enough things like that together and watching them go and feeding inputs in and having it people have tried experiments like that and get some interesting results, but nobody knows how the brain works at all. Don't let anybody tell you they do. They don't really. I mean, they got they got a little bit. If you cut out this part, this behavior happens. But the next step, therefore, we imagine there's this mechanism. Nobody has any idea what the mechanism is of anything, as far as I know. It's a very interesting problem, and it's great to work on, but if you want to spend your whole life working on a good problem and not necessarily come up with an answer, that's the place to be. It's a hard place. But Patrick Winston will come talk about this in a few weeks, and he will give you the state of the art and some really good perspective. He's very good on this. So I'm going to talk this through with you for a second. How do we make a machine that accepts the reverse? I mean, this machine goes through forward, right? 0, 0, 0, 1, 0, 0, and we accept. If we want to accept things in the reverse order, and we want to kind of use this machine as our template, well, now we start the string on the left side, but the reverse one, we're going to start it on, in some sense, the right side, right? So the first symbol we're going to look at are the symbols that are at the end of these strings. Where are those symbols? Where could they be? You might end up here if you accept. You might end up here if you accept. Or you might end up, that's it, 2 places. That means if you want to accept the reverse of these strings, you're going to need to be able to start either here or here, start at the end, and work your way backwards. And where do you have to end up? You got to end up where this machine started. You got to end up back at the beginning. So the new machine is basically going to run this machine in reverse. We're going to take all the arrows and turn them backwards. In addition, we're going to allow us to start at either of the final places where we could end before, and we're going to insist that if we accept, we only accept strings that end up where we started in the original machine. So our new final state becomes the initial state. A new initial state needs to be both of these. And all the arrows need to reverse. And that machine will mimic exactly what we mean. We mean to be able to start at a final state, go back along the arrows in the opposite direction, and end up in the initial state. When we do this, when we do surgery on this machine to make this happen, it's not going to look like a deterministic machine anymore. It's going to look weird. And we have to interpret it. It's going to end up being a non-deterministic machine. And since we know how to convert those to deterministic machines, we'll be able to convert it back. So that's where we are right now. It's a relatively complicated idea. So let me stop for a second for questions, and then we'll actually do it, and that might help you ask some more questions. Yeah, Joe?
Isn't a kind of trivial semantic solution to this reverse thing, like we just use the same machine, it's just in our mind's eye we're reading right to left instead of left to right?
Yes, but then technically, how do we actually come up with a new machine that's going to do that? Because it's possible that semantically it's true. It seems kind of straightforward just to go reverse on this machine. But this machine's got two places it can end. That's the reason I put the extra final state in, because I wanted you to realize that it could have more than one place it can end. And then reversing it needs to be able to reverse from either here or here. But a real finite state machine has one start state. Now we're going to have two start states. That's not allowed. Maybe having two start states gives us extra power. It doesn't, but that's what we have to make sure of. So you're right, it is a semantic thing, but we have to carefully make sure that having these two start states, which result in the old two final states, that doesn't give us any problems. Does that make sense? Doug, okay? Kevin?
Doesn't this machine already sort of have two start states? I mean, just in the sense that, you know, you haven't drawn an arrow into it, but the circle on the very far right, you could start there just as easily.
Yeah, that's true, because these happen to be equivalent. But that's 100% true. But technically, I could have just come up with a machine that has three completely distinct final states. And the start state might not have been any of them. The start state doesn't have to be one of the final states. So you're right, but I could have come up maybe with a better example where that objection wouldn't hold. That's a good point. Other questions? You guys want to see? Should we go ahead and do it? Let's go ahead and do it. Let's make the new machine. We'll do it over here on this side. We need a new start state. But you're only allowed one start state. So here it is. It's called start. But you want to be able to start either here or here when you're going backwards, because these are the places where you ended in this machine. So how do you start either here or here? Start here or here. I'm just going to make e's. Jesus. Epsilons. On the empty string, without looking at a symbol, you decide whether to go here or here. Okay? And that makes sense because you might end either here or here in this machine. And if you want to accept anything that's the reverse, you've got to be able to handle strings that ended here. Then you would start in this one. And if strings ended here, you'd start in this one and you work your way back. So this way you handle all possibilities. If it ended here, you'll reverse it by going to here at the beginning. If it ended here, you'll reverse it by going here at the beginning. So we've got a choice. So Sharon, you asked before whether epsilons are ors. In this context, they're completely ors. The epsilons are used just to say you can start either here or here without looking at any symbol. And now we're going to reverse all the arrows. So what happens to that? Loops reverse to themselves, right? So that stays here. And this goes this way. And this goes... Correct me if I make any mistakes here. Did I get them all? What about this? Look at this interesting thing.
Which you don't have anything going to the dead, so you're never going to get that.
So now give this.
Remember in graph theory we called this its own strongly connected component. It's got no connection to the start state. There's no reason to draw this in. I'm drawing it in just to show you that technically you really do it, but it just disappears. I want you to notice this because there's something really interesting about this reversal. Why am I spending so much time on reversal? I think it's a great way to introduce non-determinism. And there's a really, really cool thing about reversing machines that I'll tell you when we're all done. And it relates to the fact that sometimes when you reverse machines, pieces get cut out. And we'll talk about that later. All right, so what about, here's the machine all in reverse. Here's our start state. The only thing that's left to do is indicate the final state. The final state is a single place where the old initial start state used to be. Because that's where we started. Now we want to make sure we always end there. So that our last symbol becomes the first symbol of the old one. So that's over here. This was the old start state. So this new machine accepts strings where every single one has at least 2 zeros, not following it, but preceding it. Let's look at it and make sure. Well, if you go here, you can get a bunch of zeros. How do you make sure that you get all the strings? Here's 2 zeros. Then there's a 1. Can you get every single one? What about this one? Oops. Let's find a path in this machine that accepts 0, 0, 0, 1, 0, 0, 1. Where do you want to start? It's not a good idea to start here. It won't work. But you got a choice. As long as there's one way to go in a non-deterministic machine, you're OK. And we considered all the different ways. And here it is, because in this machine, if you went forward on this, you would end up here. So when we go backwards, we start here. And we go, well, we got 2 choices. Which way do you want to go? Stay there once, then go 0, 0, and then there is a 1. Do we go here? Go back here, 0, 0, 0, 0, and then there's a 1, and then we're done. And if you look at it carefully and you make enough of an argument, you could write down a little English paragraph to explain why every single string that has at least 2 zeros before every one has a way to get through this machine and end up here. And in fact, there's no other strings that can ever end up here, because the only way to get to this final state is previous 3 symbols have to be, the one before it has to be a 1, and then zeros. And if you have zeros at the end, you can tag those on. That doesn't hurt. So you can prove or write down or explain why this machine really works. But it's a non-deterministic machine. Everyone agree? Because we went backwards. When you reverse arrows, you create non-determinism. It was true that you had to have only a 0 and a 1 coming out of the states, but when you reverse them, the zeros and ones that come out end up being equivalent to the zeros and ones that used to come in. And it's perfectly OK to have 2 zeros coming into a state. That's a deterministic machine. But when you reverse the arrows, it becomes a non-deterministic machine. What's more, these E transitions are non-deterministic by nature. So here we've got this very, very non-deterministic machine. And what I want to do to complete this example, and it'll be good practice, let's take this and turn it into a deterministic machine by the method we used yesterday, and then see if we can interpret it, and by mechanics of this reversal process, come up with a machine that actually solves the problem of everyone having 2 zeros preceding it, a problem that seemed hard at first, and then we'll just have it staring at us and we'll try to figure out what it means. It's kind of cool. You come up with this machine and then you can interpret it rather than having to come up with the idea first and write the machine. And this idea can get very, very deep, where you actually can come up with solutions to problems that you might not have been able to come up with on your own at all. And it's a very, very powerful tool.
So the redundancy is still there, right? With how that we don't, like before we did the reversal, we didn't need one of those end states. It looks like we still don't need one of those end states.
That's true. You can make this a smaller non-deterministic machine. But I should have mentioned also that there is no notion of a minimum non-deterministic machine as there is with a deterministic machine. With a deterministic machine, there really is a unique minimum. But for non-determinism, it's, I guess there might be many different ones that have the same minimum number of states. You don't have that unique one. All right. Yeah.
With
Doug.
the non-deterministic machine, are we always only going to have one final position? Like in the
Yes.
deterministic, we've got
Yes. Yes. Why is that? Doug asked a question. If you do this reversal process, the reversed machine always has just one final state at the end. Why is that? It's because it corresponds to where you started in the initial machine, which is the initial state. Because there's always only one initial state. So when you reverse it, the final state takes that place, and there's only one final state. I should mention, though, that when we convert this to a deterministic machine, that we're going to get more than one final state. So it's very easy. In fact, you can always make a deterministic machine, you can always make a non-deterministic machine that has one final state. You can always take all the final states you normally have and have E transitions going to a single final state. Right? So there's never any reason to have more than one final state in a non-deterministic machine. But in a deterministic machine, insisting on one final state actually takes away power. That's a way to cut off half a brain of a finite state machine. Say you have only one initial state to start in, and you can only have one final state. That's not powerful enough to get all the strings that you need to get. And it's not at all obvious what subset of the finite state machines those kind of machines actually accept. It's not obvious at all.
If we were willing to just have more intermediate states, could we still do the same thing?
No. No. Limiting the number of final states to one restricts the sets that you can accept. It's a subset of the regular sets. You can't get all of the sets you normally get. It's not, well, we're getting off track, but I could explain why in 5 minutes. And maybe if you remind me later this lecture, I'll get back to it. I can give you an example right off the bat, and you'd say, oh, yeah, for sure.
Shai, is this machine over here on the right supposed to be a deterministic machine?
It is supposed to be, yeah.
Okay, it says every one has at least 2 zeros following after.
Right.
Doesn't this only allow for a single one? I mean, you're going back to... Oh, I'm sorry. I misread it. My other question was on the left. You have this dead state, and you're able to get out of the dead state.
Yeah.
Into the dead state.
Right.
You know.
Right. Right. So it's like
A birth state.
it's a birth state. There's no reason to draw it in. There's no way to get here at all. It's like a secret room in a cave, and there's no passages there.
Okay.
It's like that kid that got stuck in Purgatory Chasm yesterday. Nobody watches the news because it's so boring. Are you in there? Yeah, I'm stuck. All right, you guys need to do some work now. We have this non-deterministic machine, and I want to turn it into a deterministic machine. And when we do, we're going to stare at it and see if we can make sense out of what we've created, and then see, oh, that's how I should have done that preceding 2 zeros before the 1. And hopefully it'll make sense, and we'll appreciate the neatness of this reversal procedure. Before we do it, I just want to point out that what we did here in this particular machine for reversal was completely general. We could have done it on any machine. It didn't have to be just this machine. You can do the reverse of any machine. So this example is essentially a proof that regular sets are closed under reversal. Okay? By the way, there are much easier proofs of this when we get into other ways of describing regular sets. There are easier ways to see it. But this is one way, and it leads into this nice example. So let's go ahead and do it. Let's convert this to a deterministic machine by keeping track of what this non-deterministic machine is doing. We start in the same start symbol. And now we can see either a 0 or a 1. Where might this machine end up if the first symbol it sees is a 0? This machine is going to remember where this machine might end up after it sees a 0. Well, this machine might start here, or it might start here. If it starts here and it sees a 0, it'll end up in state A. If it starts here and sees a 0, it'll end up in state D or state C. So on a 0, where might this machine be? In a possible one of any of the states in this set, A, C, D. This machine is a finite state machine that's going to be deterministic. It's going to keep track exactly where the non-deterministic machine might be after reading any sequence of symbols. So after reading a 0, it's going to end up in either A, C, or D. And after seeing a 1, it's going to end up, well, here. If it started here, there's no 1. And if it started here, that's interesting. So what do I put here? I leave it empty. Call it the empty set. Somebody asked me about this yesterday, and I wanted to make sure that I did an example of this. There's none of these places it might end up in. I think Todd asked me at the end of the day whether it's 2 to the n or 2 to the n minus 1. It can really be 2 to the n because there's none of these places that it might end up in. It won't possibly get into A, B, C, or D. So it's going to go nowhere. Now, from nowhere on a 0 or a 1, you end up nowhere. And that's just what you said. So Chris is right. This empty set is what we normally call a dead state. Good. Well, that's nice. At least we don't have to do any further exploration from here. But we do have to do exploration from here. There's zeros and ones here. On an ACD, if you get a 0, where can you end up? A, D, C, or B. All of them, right? All right, if you're not sure what's going on here yet, ask yourself the question. If you saw 2 zeros in a row starting from here, where might you end up in this machine? And the answer is A, B, C, or D. Any of those places. To go to A, 0, 0. To go to D, 0, 0. To go to C, 0, 0. To go to B, start here, 0, 0. You could end up in any of those places. So by the way, should we accept 0, 0? It ends up either in A, B, C, or D. Should we accept it? Yes. Why? Because it can end up in A. That's very important to realize. When we're all done making this machine, and we're going to be all done in 2 more minutes, how are we going to identify what the final states of this deterministic machine are? They are any states that contain 1 or more final states from the original. In this case, since there's an A, this is going to be a final state. And I'm going to mark it so right now, so you remember. And so is this.
But so is S.
No, I don't think S is.
Isn't the empty string accepted by R?
Well, you've got the epsilon move that's going to take you immediately to A.
But not in this state. I would have had the start state be AD.
I mean, have it be the combination. Yeah, you could do that. Yeah, this is a technicality about the empty string, whether you want to accept it or not. So if you accept the empty string, we'll add it in here with a double circle. And if you don't, you leave it blank.
Otherwise, we could have 2n plus 1 states here. That's too many.
Right, right. We don't want an extra one. Right. Or you could start with AD at the beginning, too. That's another possibility. All right, let's continue. So, but we are accepting the empty string, so I'll put a circle here. That's fine. No circle, double circle here, because this has got no A in it. Now we got to get a 1 out of ABCD. Where do you go with a 1 out of ABCD? All right, ACD first. Come on. Where does it go? No place. Where does this one go? How about this one on a 0? That's easier. It goes to the same place. It goes ABCD. A fast way to do that is if ACD went to ABCD, then certainly ABCD is going to go to at least ABCD. And it can't go to any more because it can't get to the dead state or the S state. So you can kind of do that a little more quickly. But what about 1? 1 doesn't go to a dead state here. 1 goes to some real place. It goes to A combined with D. Good. That's another final state. Well, that's what Chris was saying before. Yes. Everybody who said isn't that the same as a start state? Yes. But let's just stick with this more mechanical general way, and it'll be OK. It's not going to be wrong. Maybe a little longer than necessary. All right, AD on a 0 goes where? Check it out and tell me. ACD is right. And AD on a 1 goes to the dead state. I think that's it. This is a deterministic machine that accepts all binary strings that in front of every one appears at least 2 consecutive zeros. How does it work? Does it make sense? Can we make sense out of it now that it's here? I mean, here's the answer. Let's interpret it and make sense out of it. Who wants to try?
So is ACD like the union of ACD? How should we interpret the commas?
All it means is that if you ever end up here, then the string that you read could have ended up in the original machine in either A, C, or D. So it's the union only in that sense. But I don't think you can go any further with that analogy. So what's going on? Right, and everybody noticed that these two states are identical? I think that's true. So we could have just started from here. I think that would have been fine. But that's neither here nor there. How do we interpret this? Let's just go through it. Let's go through some examples. Presumably, before everyone, there's got to be at least 2 zeros. So what does this represent? We saw 1 before there were 2 zeros. You're going to die right there. That makes sense. Okay, so you start with a 1, no good. You got to start with a 0. So here's a 0. Fine, we saw 1 0. Let's call this state, I just saw a 0. Okay? Let's call this state, I just saw 2 consecutive zeros. I saw a 0. I saw 2 plus zeros in a row. Why did I say 2 plus zeros in a row? Because if you get another one, you stay there. So this is the last 2 symbols I saw were zeros. The last symbol I saw was a 0. If you get here, then you're allowed to have a 1. Otherwise, you're not allowed to have a 1. If you get a 1, okay. If you get a 0 after that, where do you go? Back to the thing that says, I saw a 0. Right? Then if you see a 1, you're dead again. But if you see 2 zeros or more, you can go back and continue. It isn't so hard once you see it in front of you. And if we had done it from scratch, we probably would have come up with this idea. But right at the beginning, the first one we did seemed a lot easier than this one. Even though they really weren't, one wasn't really more difficult than the other. But this reversal shows it mechanically. And it's nice to have this tool that reversal always stays regular. Okay, are there questions about this? Teresa?
What does it mean that I saw a 0 and I saw 2 zeros are both except state? I guess I only get the final except state, but why are those 2 intermediate states?
Because the only time you don't want to accept is if there's a 1 that came without the 2 zeros. So if there aren't any 1s, it just doesn't hurt. So any collections of zeros you're going to accept anyway. Right. So it's a semantic thing. We're not saying that there has to be a 1. They're saying that if there is, then there's going to be zeros in front. So it's okay, and we really should make these accept states.
Same number of states for reversal? In the minimal digit?
Yeah. Todd asked the question, what happens when you reverse a machine? What do you think happens? Well, when you reverse it, just the arrows go backwards, and we add a start state. So that's just adding 1 state. That's no big deal. But then we had to convert it to a deterministic machine. And here we got lucky that we didn't add too many. But it is conceivable that in this non-deterministic to deterministic conversion, we would have used all the subsets here, and the number of states would have increased from n to 2 to the n. And we might not be able to prune it down. So it's very possible that the reversal of a machine uses a lot more states than the machine itself. But here's something really cool. It's really cool because to this very day, I have never really sat down and figured out why this works. And to this very day, I don't know any paper that refers to this. As far as I know, it's just folklore of theoretical computer science. And here's an interesting fact about reversal. Remember I mentioned many times already that there's a deterministic machine that's minimum. And if you find that minimum one, that's say 4 states big for any set, then they're all identical. Then all those 4-state machines, look the same. There's a unique minimum finite state machine. And I mentioned it's worthwhile to know how to get that. Because you might not have it to start with, and you want to keep your program that simulates these machines as simple as possible. Now there's lots of algorithms, and I'll teach one in another week or so about how to do that. But there's one kind of a folklore algorithm that isn't very efficient that deals with this reversal technique. But it's just so cool that you should know it. Here's what you do. Say you want to minimize a machine, like the one we started with. Go ahead and reverse it just like we did, and then convert it back to a deterministic machine just like we did. And here's what you get. Okay? And now do it all again. Reverse this again, convert it back to a deterministic machine, and then see what you got. Now what you got then is a machine that does the same thing you started with, right? Because you just reversed it twice. But interestingly enough, as long as you're careful to chop off all the things like this that aren't connected anymore, then when you're done doing this, double reversal, you have the minimum finite state machine. So like I said, as far as I know, that's not published anywhere, and it's just folklore. And I do remember getting an email from a co-author of mine who's really an expert on this stuff, Sheila Greibach, and she explained to me very briefly, oh, you see what's going on, of course, and she described it in a few sentences. And I didn't quite see it that moment, and I never went back and looked at the email and tried to figure it out. But it might not be hard to figure out, I just never did it. But it certainly is interesting, and it does seem a little bit surprising. Anyhow, questions about this? Yeah.
Question. The epsilons, I noticed you just got rid of them, sort of skipped over them since they are sort of a free move, so to speak.
Right.
So do you do that in all cases? I mean, do you ever see epsilons still being used in the deterministic machine?
No, no, no. Deterministic machines can't have epsilons. Epsilons make machines non-deterministic. So, but if you have non-deterministic machines with lots of epsilons in them, you can always convert them back to determinism using this trick. Basically, you know, if I say what's going to happen on a 0, if there's any epsilon moves, I got to follow those all the way to the end. Say there's a lot of them, spread them all out, and then look for the 0s and 1s. So I did this example with epsilons partly to show you this reversal and partly to show you that the presence of epsilons can be taken care of with the same trick we use to take care of non-determinism, just by looking forward. But normal deterministic machines wouldn't have them. Okay. Yeah, Peter.
If you do the reverse, are you always going to lose the dead zone?
Yes.
Are there other conditions that would...
Yes, there are other... Right. So Peter's thinking just the right idea. The question is, what do you lose? What do you lose when you do reverse? And you clearly lose dead states because all their arrows reverse back and there's no way to get to them. But you might lose other things. And characterizing exactly what it is you lose ends up... You lose the things that are not identical. That's what ends up happening. It's kind of neat. Well, like what are you going to lose here? Does everybody see that you kind of lose this state on the way back? Right? Because the arrows go back in here. And this is no longer an initial state, or it doesn't have to be. That's why when you're all done, this disappears and you get a four-state thing. I don't really understand it, so I'm just blabbing now. But I'm sure there's some nice idea behind it if I thought about it. Okay.
Well, what makes you think it's true then?
Because somebody told me who I trust. And because I tried it. I mean, well, what makes me think it's true? Right? Proof by example. I've done it a few times and it seems to work. I am not convinced it's true. I would not bet a lot of money that it's true. Possibly it's not true. But the person who told me is very reliable. She's quite bright, and I trust her. And I never sat down and convinced myself. So I can't claim that it's true, but I think it is. By the way, that algorithm is not so good because in the reversal process, you can have this exponential explosion of states. So we don't use this method. We've got to have a better method. And there is a better method. There's a polynomial method that uses dynamic programming strategy. We'll get to that. Regular sets are closed under all sorts of things, as I mentioned. And Dimitri pretty much touched on this yesterday, but I want to touch on it a little more now because the reversal was a tough proof using the machines. And it led us into all sorts of alleyways. But now we're going to do ones that are a little easier. The complement was a little easier. Let's do union. If I have a set I give you, like the set of strings with an even number of zeros, and I have another set of strings containing 1, 0, 1. Both of these are regular sets. Both of these have finite state machines. You could draw them right now. You probably did examples just like this in recitation yesterday. You have a million examples to do on your problem set. You can draw these even on the spot. It doesn't take too long. This is 3 states or 4 states. This is 2 states. Draw them up. What if I said, now, give me a finite state machine for the set of all strings that either have an even number of zeros or contain 1, 0, 1. If you try to do this from scratch, you start keeping track of 2 things simultaneously. And you can get confused. But if you raise your level of abstraction a little bit and think of this as simply the union of these 2 sets, either this or this, here's an automatic way to get it. Give me the machine for the first one. Give me the machine for the second one. I'll throw them in here. Here's the machine for even zeros. I don't care what it looks like. Here's the machine for containing 101. I don't care what it looks like. You guys fill it in, make it up. Here's a machine that accepts the union of those. New start state, epsilon to here, epsilon to here. Take all the final states from here, all the final states, all the final states, epsilon to a single final state. Everybody see what I did? I just said either go here or go here. If there's a way to accept the string because it has an even number of zeros, then choose this way. Go through the deterministic machine, and when you're all done, jump out to a final state. If there's a way to accept the string because it contains 101, then choose this way and end up jumping out to a final state. And if it's neither one of these, then you'll never get to a final state because no matter which way you choose, you can't get through the machine. So this funny-looking non-deterministic machine is the union of these 2. And that's it. Now, converting this to a deterministic machine might make the resulting machine look a little ugly. Now, did Dimitri talk about taking the product of 2 machines? If you went through the trouble of converting this non-deterministic machine to a deterministic machine, you would do exactly what he calls the product. All that does is pair these states together. Because on a 0, 1, you're either in this one or this one. And on the next 0, 1, you're either in this pair or this pair. It just pairs up. But you don't even need to know what he talked about. Just convert this to a deterministic machine, just like we convert all non-deterministic machines to a deterministic machine. And it's one more power of non-determinism. In a second here, we can see that union is a closed operation without having to deal with any more complicated argument. Being able to build on the fact that we know non-determinism is equivalent to determinism. All right, questions about this?
The intersection is not so neat.
No, the intersection, you can't do it this way, but you can do intersection a different way. So we'll talk about intersection in just a second. Everyone know how to do complement? Complement is pretty straightforward. You toggle the final and non-final states. Intersection's the next thing. We'll talk about it in a moment. Before I do intersection, what if I said, I want to accept the set of strings where some prefix of the string, some first part, has an even number of zeros, and then the remainder of the string contains 1, 0, 1. That's called the concatenation of these 2. Take any string from this set, any string from that set, connect them together. The set of all those strings is the concatenation of these 2. Take all the strings with even number of zeros, connect onto them any string containing 101. All those strings are in the concatenation. How do I make a machine that accepts the concatenation of these 2? I just take this machine, good, and then take all the final states of that machine and have an E move to the initial state of the second machine. So first I look for one string, and then I look for the other. And I can decide or guess when to use that E move to start looking for the second one. I can stay on my first one looking for a final state, or I can jump over. And that E move is very important to the power. And if you get rid of the non-determinism, you'll get perhaps a complicated machine that's deterministic. But again, you can see that it's closed under union and complement and concatenation by this non-deterministic idea. Okay, Doug, you have a question? Okay. Teresa, you're thinking about something?
Why do you say that E move is so powerful?
Because let's do a real example. Maybe this will help. Let's concatenate these 2. All right, so Teresa, you have to help me. That's what you get for asking questions. Let's make a machine that has even number of zeros. You start here.
Okay. 0 goes to the next.
0 goes to the next state.
And then go one more.
Well, that means I have an odd number of zeros.
Okay. Go back.
Go back if I have an even number of zeros.
Okay.
And that'll be my final state.
Okay.
And if I get a 1 here, I can stay. Right. And here I also stay. So this is even number of zeros. Okay? Including zero zeros. Including no zeros. And what about containing 101? Here's 1, 0, 1. This is the beginning. If I see a 1 and an 0 and a 1, then I stay there and I accept everything. But what if I get a 0 here? Stay. What if I get a 1 here?
Back to the beginning.
Yeah?
Go to itself.
Oh, wait.
I think I need to stay because I've already seen a 1. Right? We did one of these last time, I think.
Right, yeah.
And then here, 1, 0. If I get a 0, that's back to the beginning. So here's 1, 0, 1. Here's even. Now let's say I want to accept all strings whose first parts are made up of things that have even number of zeros, and second part is made up of things that contain 1, 0, 1. So I'm going to have the initial state start here, and I'm going to take an E move from the final state of this machine to the initial state of this machine. And now, this machine can churn through looking for an even number of zeros, and whenever it feels like, it can either keep looking and continue, or switch over and start looking for the second half of the string that contains a 1, 0, 1. This is a powerful choice, because it isn't obvious when to make this choice, but as long as it has the ability to make it anywhere it wants, it can always find the right place to do it. And there's never any way it's going to end up in this final state unless the first half that it made its point to make the decision to move, unless the first half had even number of zeros and the second half had a 1, 0, 1 in it. So it will accept just the ones we want. There's always a way to accept the ones we want, and this E move tells us when to do it. If we went ahead and converted this all to a deterministic machine, it would be deterministic and less obviously magical. All right, does that make sense? A little more? Seth, you thinking about something? Or you? No? All right. Just looking thoughtful.
It's just like a real simple notation for doing a million different things.
Yeah, it's really cool, yeah. Here. You guys know how to do intersection, and you know how to do union and complement, right? So remember this rule? Remember that from who knows when? What's that called? Anybody remember? De Morgan, good. He's rolling in his grave with happiness. Yes, Doug remembers me. Right, that's De Morgan's law. And it's a law about sets. You can make a picture of this and convince yourself. It's also a law about Boolean algebra. It works with ands and ors and nots. The key thing is, if you've got two machines, one for A and one for B, you can get a machine that does their intersection by doing this stuff. You can complement A and complement B. You guys know how to do that, right? Toggle the states. Then union them. You know how to do that? Do your two E transitions. Then complement the result again. You have to take your two E transitions, convert it to a deterministic machine before you complement it, because we only know how to complement deterministic machines. So there's a lot of work here, but at least in principle it can be done. So now it's closed under intersection. And you should always know that union, intersection, and complement, you can't have just 2 out of the 3. If you have 2 out of the 3, then the third one's also closed. Okay, because intersection depends on the other 2, and union depends on the other 2. So either they all are, or just one of them is. And that's going to happen in the levels above finite state machines. Finite state machines, like I mentioned, are closed under most things, so here all 3 are. This is not the nicest way to do it, though. If I actually made you come up with the intersection using this method, it's a pain in the butt, right? You do the complement, take the union, convert it to a deterministic machine, complement it again. Anytime you have to move from non-determinism to determinism, there's an exponential potential. That's a pain. Nobody likes that. No good. So I'm going to show you a better way to do intersection, which is similar to what Dimitri did last time, this idea of the product of the two. And it's very natural, and we'll do it with, maybe we'll do it with these 2 examples.
Are there programs that do all this?
Ooh, yeah, there's a link I just put up on the course site. There's a woman named Susan Roger who works at Duke, who specializes in pedagogical tools for theoretical computer science. And she has a lot of good work that she's done with her National Science Foundation projects. And you can download it and use the tools and play with the stuff instead of with your pen and pencil with a machine. Yeah. Lots of different things. Call this A and B, and call this 1, 0, 1. Well, let's call this, I need another alphabet.
Why not E and O?
I'll do Hebrew, but nobody knows Hebrew letters.
Do like later in the alphabet, like X, Y, Z.
Oh, you're good one. Okay, there we go. Here's the even number of zeros. Here's containing 1, 0, 1. Here is a final state. Here's a final state. Let's find the intersection of these two in a more direct way than that abstract proof I just gave you. Here's what we're going to do. And it's going to reinforce non-determinism one more time. Let's keep track of what both these machines are doing as you read symbols. When you start, where are these machines? In what pair of states? In A and X. Okay? Let's forget about final states for now, or how we're going to interpret this. Let's just use this to simulate these being run simultaneously. We start off in being in both A and X, and now in a 0, where do we go? B, X. And on a 1, AY. Good. I'm going to do a little more of this before you get bored. How big might this get? Every new state in my new machine is going to have a pair of old states. So we have 2 states here and 4 states here. It's going to be 8 at the most. It might be all of them. It's possible some might not show up. But we might have 8. You're probably bored. Who wants to go see 8? But let's just do a little bit more just to make sure everybody gets it, and then I'll show you how to finish it up. From BX on a 0, where would you go? A, X. That's not bad. From BX on a 1, where do you go? From AY on a 0. BZ?
Oh, AY.
AY and a 0, BZ? All right, everybody see how to complete this? Sooner or later, you'd come back to states that are already there, and you finish your whole machine, you get a deterministic machine. How do we interpret this? You can interpret this to do union or intersection in a way different from the way we did union and intersection before. This keeps track of where both these machines are. If you want a string that's either in this one or in this one, then the final states in here should be any state that has either a final state from here or from here. So AX would be a final state for doing union, because you can end up in A. AY would be a final state, because you can end up in A. Anything with a W in it would be a final state. But if you wanted the intersection of the two, you have to look through these states and find, in this case, only a single state, the state labeled AW. So if we continued this, sooner or later AW would show up. And that would be the only final state in the machine for the intersection. So this product, this is called the product of these two machines. It's done in a very similar way to non-deterministic calculation of turning it into a deterministic machine. But in this case, you're only keeping track of simultaneous machines, 2 states, not a subset. So it doesn't grow quite as large. It's only the product of these two instead of exponential. And what's more, you can do either union or intersection depending on how you interpret the final states. So that's another way to do intersection.
So the second option of doing it, the reason that we would do that is just to have another way to go at it, or is there...
The reason you would do this, because let's say you were writing a program to do it. The other way wouldn't be your choice, because the other way explodes exponentially. If you were building a program to do it, the way to do it is to take the product of these two and just have pairs of things in your states rather than subsets of things in your state. Because if you're just unioning or intersecting 2 machines, that's a much more specific thing than taking a non-deterministic machine and converting it to a deterministic one. There you have to keep track of every possible subset. But here the subsets are always pairs. So we should notice that. Yeah.
You didn't do the non-deterministic intersection. That's, you didn't. And.
We just did that now. That's this.
Deterministic.
Right, right. Well, we showed that if you have two machines for A and
You did
B.
the union, this with multiple.
Oh. Is there any way to do intersection non-deterministically?
Yeah.
Only indirectly. First you do the two complements.
Okay.
Then you do the union, and then you do the right. There's no other right. Non-determinism does not mix well with intersection. Non-determinism mixes well with ors, not with ands. And this is an idea that's going to come all the way up in Turing machines. And I'll show you something that's, well, you brought it up, so you're getting this 2-second digression. But you know that non-determinism means you have a 0 coming out of here and another 0 going in another place. And we define it to mean we accept any string if there's a way to get to a final state through here or through here. Why didn't we define it if there's a way to get to a final state through both of these? Why didn't we say and instead of or? Somebody in their gut instinct might have just said, well, I'm barely understanding what's going on so far, so I'm not going to ask that question, right? But that's a natural question to ask, right? You got to say, why make this or? Why not make it and? I try to motivate why we made it or, because if you do this reversal backwards, it's kind of what we want. You want to start here or here. Or is more natural. But people do define this as and. And sometimes you even mix finite state machines, where some of the states are labeled or, and some of the states are labeled and. And those are called alternating finite state machines. And the way you define whether you accept a string in those is that anything that goes through an or state, there has to be some path out of it that gets to a final state. Anything that goes through an and state, all the paths that go out of it have to reach a final state. It turns out that making a finite state machine alternating like that also doesn't give it more power. And that idea of an alternating idea goes up to Turing machines. So we may talk about that much later in the course again. But it's a good question to ask, and it's an interesting point. For the rest of the lecture, I'm going to stay away from some gory details, which we've been spending time on up till now, and talk more big picture of where we're heading for the next lecture, and then I'll fill in the details in. So here's where we are. We talked about finite state machines, non-deterministic machines. We found out that non-deterministic finite state machines can be converted to deterministic finite state machines. So either one of these are okay way to look at these kind of sets. There's going to be a bigger set of connections. We're going to connect this to something called regular expressions, which you've seen in other contexts. Specifically in web programming, you see regular expressions a lot. In any kind of pattern matching, you see it. Regular expressions is another way of describing the sets that finite state machines can accept. They're identical to the finite state machines. That's not obvious. But tomorrow, Sunday, I will show you how to convert any deterministic finite state machine to a regular expression. So there'll be a connection between here and here. So this is not yet, but this we've done. And then I'm going to complete the triangle by showing you that any regular expression can be converted to a non-deterministic finite state machine. So these are all three different windows to the same picture. And in computer science, you desperately want 3 different views to the same thing, because depending on the view you have, certain things seem easier. And the more views you have, the more tools you have at your disposal to make important discoveries. So we're going to do this triangle. There's a fourth thing called regular grammars, or sometimes called linear grammars. And these are also equivalent to all these 3. And we're going to fit it into the picture by showing an equivalence to deterministic machines. So that will fill in this picture of looking at finite state machines from all the different possible ways. There is no such thing as an analog for regular expressions as we go up the hierarchy. It disappears. But there is such a thing of non-determinism, and there is a grammar analog. The grammar analog and the machine analog rise all the way up this hierarchy, all the way to Turing machines. And that's what's sometimes called the Chomsky hierarchy. The grammar and the machine parallel all the way up the line. And it's really interesting because grammars and machines don't look alike, but they come in pairs. All right, questions about where we're headed with this? All right. Second big picture. we talk really briefly about what isn't a regular set. Okay, what can't be accepted by a finite state machine. And a lot of different ideas came up. Somebody said Fibonacci numbers in binary. That's true. Not acceptable by a finite state machine. Equal numbers of zeros and ones. Anything that requires counting or arithmetic or more than finite storage, no way to do it. So none of those things can be done. The question is, what things can be done? Well, things that you can write regular expressions for can be done. Things that I give you lots of examples on the homework can be done. It would be nice to have a method to show that you can't do something. Because otherwise you just go home and you try really hard and you come in and you say, I can't do it, but that doesn't prove to me you can't do it. And proving you can't do something is always harder than proving you can do it. Because once you've done it and show me an example, you're finished. But to show me you can't do it, you can try an infinite number of examples and I'm still not satisfied. So we need a trick. And I want to introduce this a little bit because it's a nice, we'll go through it again in detail, but at least it's a nice way to kind of end the day. You don't have to take notes on it. We're just going to have a discussion. So here's the discussion. Here's a set. 0 to the n, 1 to the n. It includes the empty string. It includes 0, 1. It includes 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, etc. Okay, it includes all the strings that have an equal number of zeros and ones that start with zeros and end with ones. There's no finite state machine for this. Let's convince ourselves. Let's try to make one. If I see a 0, I go to a new state. Now remember, I've seen 1, 0. And if I see a 1, I go back here and I accept. If I see another 0, I go here. And if I see a 1, I go all the way back? Right, I go back twice. And a 0 out of here, I die. And any arrows I don't put in, I'm dead. Well, that takes care of 2 of the strings. Or 3 of them.
Back on the 1.
Here?
Yeah.
You tell me, Sharon. Why wouldn't that work? Because it would accept things that I don't want it to accept. What else would accept if I did that? It would accept 0, 0, 1, 0, 1. This is a really important point that Sharon made up. A lot of times you say, oh, I can do that, and you include all the things you're supposed to accept, and you think you did it, but you included lots of things that you weren't supposed to accept. And a lot of times, sets are easy because they're so inclusive. The more you include, the easier it is to make a decision. It's like if you're a bouncer at a bar, and you're not very picky, and you let most people in, then there's not so much work you have to do. And same thing here, if we just, I don't know what I'm thinking. If you just go ahead and put all the ones back in here, it includes lots of things. Lots of things that you don't want it to. Yeah, Brian?
I have a totally unrelated question about the notation with the
Yeah.
exponents there. That really threw me in the book. Normally if I see 1 to the 5th, I think 1, not 1, 1, 1, 1.
Yeah.
So
right.
Is that just a convention for
Yes.
this kind of work?
Yes. In this book, you will, I'm not going to say never, but you will hardly ever see this mean 32. All the symbols in this book are, for the most part, strings. And exponentiation in a string just means repetition.
Okay.
And it should have thrown you the first time you saw it. But try to get used to it. It's 98% of the time just repetition.
So 0 to the 0 is an empty string then?
Yeah. But you can see how often I've used that. Yes, you're right. Absolutely. Good.
I thought chapter 0 was that really helpful.
Chapter 0 makes it very clear.
It emphasizes it. It says, be careful, right? Is something?
It just goes over.
It just goes over
definitions.
Uh-oh.
No, I'm not just
Oh, in Clover. All right. So if we kept trying to do this, what would happen? Here's 3 zeros. 1, 1, 1. Right, it doesn't look very finite. This is a nice infinite state machine. While I'm saying this, what do you need to add to a finite state machine to make it more powerful? If you gave it an infinite number of states, that's a Turing machine. Right? So you can't do that. You know what you need to give? What can you give it that's less than an infinite number of states? You could give it like a little data structure to work with. If you gave it an array, Turing machine. If you give it a stack, not a Turing machine. If you give it 2 stacks, yes, a Turing machine. It's a really neat hierarchy.
This is all news to me.
It's all news. I'm just telling you right now.
What's the big deal between 1 stack and 2 stacks?
We can do a lot more with 2 stacks than with 1 stack.
I gotta give me another stack.
This is the big picture. We're not going to talk too much about the details. All right, but I want to get back to this. So this doesn't work. I want to convince you this will never work. I'm going to convince you that if Chris Walker goes home tonight, as is his habit, and
I know he comes here.
and he spends all night coming up with a finite state machine for 0 to the n, 1 to the n. And he calls up all his friends from class, and he gets all the advice he can. And finally, about 4 in the morning, he gets it, and he's positive. He's unaware that he's just completely deluded because he's tired and he just doesn't remember. And he comes into class, and he's ready, and he says, I got it. Here's my machine. I'm ready. It's wrong what you said. All right? And I go, OK. So now we're going to have a dialogue. And Chris is a good-natured fellow, so we're going to have this dialogue right now. So my question to you is, how many states are there in your machine? Just give me a number. It doesn't matter.
24.
24. OK. So Chris says there's 24 states in his machine. Right? So now I say to Chris, OK, Chris, do me a big favor and take this string, 0 to the 24th, 1 to the 24th, and run it through on your machine for me. OK? And I push him a little further. I say, you would admit that since there's 24 zeros here, that somewhere in those first 24 symbols, you're going to have to hit a same state twice. Right? Because you start in your initial state, and you move along on zeros, moving from one state to another. And if you keep going to new states, you only got 23 moves, before the end. So sooner or later, somewhere, you're going to have to hit a state twice. You agree, right?
Yeah.
And I nailed you down because I asked you how many states were in your machine before. And then I picked this. That's really important in this dialogue. If I gave you the string before, you'd say it's got 80 states in it.
Yeah.
And
I knew one was 25.
All right, well, then I'm changing this. That's the key. Chris has to tell me first, because he said he's finished. And now I give him a string to try out in his machine. And I tell him, look, I know there's going to be a loop somewhere in this machine. Tell me the first state that gets entered twice. And tell me specifically how many zeros got read before that loop, how many zeros are in the loop, and then how many zeros and ones after the loop. So you can split it up any way you want. I don't care. Say it was 17 zeros before the loop, and say there were 3 zeros in the loop, and then the rest of the string happens after the loop. Okay, there's got to be a loop somewhere. The loop could be just 1 0, but I just picked this at random. You should actually pick this.
That was a good guess. That's exactly how.
Very kind. OK, so what's left over? 0 to the 4th, 1 to the 24th. Right. So and this is the loop. This is a part before the loop, and this is the part after the loop. There's 3 parts to this computation on the string. The part before the loop itself, and the part after the loop. And now that you've admitted to me this, I'm going to say, OK, well, now try this. Try 0 to the 17th, 0 to the 3, 0 to the 3, 0 to the 4, 1 to the 24. What's your machine going to do? It's going to do the same thing it did before on the first 17 symbols. Then it's going to loop on the next 3, just like it did before. And then it sees the exact same symbols again. So what's it going to be? Where's it going to be when it's done with these 3 symbols? The same place it was when it was done with these. It just loops. It's just going to take that loop twice. And now it continues. So if this ended up in a final state in your machine, then so is this going to end up in a final state in your machine. Right? Because they both continue from the same spot after here. They both hit that loop and then continue on. What's wrong with that? Well, you're supposed to make a machine that accepts things that have equal zeros and equal ones. You started out with 0 to the 24th, 1 to the 24th, and now I've convinced you, without looking at your machine, that your machine has to accept 0 to the 27, 1 to the 24th. So your machine's bogus. Not because it doesn't accept all the 0 to the n, 1 to the n, but because it accepts more than it's supposed to. So that's why I did this now, because of your question. The argument here forces somebody to come with a hypothetical machine, and then in a dialogue forces them to admit, oh gee, I may have gotten all the strings you want, but unfortunately you seem to have convinced me that I'm getting more than I really want. And this idea is the heart. We'll do a whole lecture on this with a lot of examples, but this is the heart of something called the pumping lemma. And it's called the pumping lemma because you're pumping up this loop. Regular sets are called regular because if you have a regular set, you can always pump it up at regular intervals and get other things in the set. They string out at very linear intervals. That's why anything that grows faster than linear is never regular. 0 to a square number, that's definitely not regular, because regular sets you can pump out at linear intervals, and squares are not linear. 0 to the anything that's not linear won't be regular. So that gives you another way of thinking about regular sets. They are linear in some way. They are very, very regular, and that's why they're called regular. All right, so that gives you a couple big picture things that are coming up. We'll do this conversion of deterministic to regular expressions and from regular expressions to non-deterministic next time, and we will start on the pumping lemma and showing things are not regular the time after that. We're going to try to finish this whole level of finite state machines in another 2 to 3 lectures. You should think of this course as being basically a week on finite state machine level, a week on the context-free grammar level, a week on the Turing machine level, and then a week at the higher level of complexity theory and decidability. Okay? Let's quit for today.